So the other day we recapped inverse functions. The main reason we did that was so we can create our inverse trig functions. So let's start with inverse sine. Well, if I draw up my sine graph, there it is. We know its domain's all real x. We know the range is in between -1 and 1. However, as it stands, it won't have an inverse because it fails that horizontal line test. And what we saw was we want to restrict the domain. We want to grab a piece of this curve which is continually increasing or continually decreasing. And there are lots of different choices we could have. But if we go with that basic idea of, hey, we'd like to include 0, and then the positives, then the choice becomes obvious. We're going to go from -π/2 to π/2. Okay, the range will stay the same, of course. So our new function, the inverse sine function, the domain will now be -1 to 1, the range swaps over, and the range will now be that restricted domain swaps over. It'll go between -π/2 and π/2. And this explains why when you plug a number into your calculator when you're trying to find an angle, it will only ever give you an answer that's an acute angle or a negative acute angle, because it's using the inverse sine function. Let's draw it. It'll be a reflection in y equals x, but because of my scale that I've done here, I'm going to do it on a separate diagram. It'll be a little bit easier. So we're going from -1 to 1 in the domain, and it's the sine curve, but now it's winding along the y-axis instead of the x-axis, but it's just that piece of it. So there's our inverse sine graph. Let's do inverse cosine. So the cos graph, let's draw that one up. There it is. Again, all real x, range -1 and 1, and once again it fails the horizontal line test. We want to grab a piece of the curve. Well, this time if I want to include 0 and go with the positives, my restriction, I'm going to go from 0 to pi. Keeps the range the same. So inverse cos x, the domain, well, the range swaps over, -1 to 1, and the range will be the restricted domain swaps over 0 to pi. And that's why when we use our calculators, it will give us an obtuse angle when we're doing cosine, because our range is between 0 and pi. So it will give us the obtuse angle. Let's draw that one. If I was to reflect that in y equals x, there we go. So it's our cosine graph winding along the y-axis. Inverse tan then, let's complete the set. Y equals tan x, draw that one up, there it is. That one had an interesting domain, all real x except, well, the first asymptotes at π/2 and then every multiple of pi after that and before that. The range is all real y. Once again, fails the horizontal line test. My restricted domain, I'll just go between these two asymptotes and then I'll get something that's continually increasing. So between -π/2 and π/2, but of course not including those for this one. The range is then all real y. And now the domain of the inverse tan function, that range swaps over, and the range, the restricted domain swaps over, and drawing that one up, that piece of the tan curve, but now it's going along the y-axis. So we get horizontal asymptotes instead of vertical asymptotes. So there's our 3 basic inverse trig functions. So some rules. If you look at that inverse sine curve, it's an odd function. It had rotational symmetry. So we know we could use this fact. Inverse sine of negative x is equal to the negative of the inverse sine of x. Inverse cos, though, is a little bit different. This is the relationship. Inverse cos of negative x is equal to pi minus the inverse cos of x. The reason why is, whilst it's not an odd function, if you look at the picture of inverse cos, what it is, it's an odd function that's been shifted up, π/2. So instead of having rotational symmetry around 0, it's got it around π/2. I'll explain where that comes from in a second. Inverse tan graph, again, if you look at that one, that is an odd function. It has the rotational symmetry. So inverse tan of negative x is minus the inverse tan of x. And the other relationship that can be useful is this one. Inverse sine of x plus inverse cos of x is equal to π/2. That's basically coming from the angle sum of a triangle. Because if you had a right-angled triangle, one of the angles would be the inverse sine of x, and the other angle would be the inverse cos of x. And so therefore the two must add up to 90 degrees or π/2. So that inverse cos one, where does it come from? Here's the graph. And what I'm saying is, if I was to shift that back down, I would end up with an odd function. It's got rotational symmetry about the origin. So the equation of that new curve, I've shifted it down pi on 2, would be inverse cos of minus pi on 2. But we're saying that is an odd function. Therefore, function negative x must equal the negative of function x. If I substitute that in, inverse cos of negative x minus pi on 2 must equal the negative of the inverse cos of x minus pi on 2. Playing around with that, and there's our relationship. The inverse cos of negative x is equal to pi minus the inverse cos of x. So that's where it comes from. Some alternative notations. Inverse sine of x. You'll also see this one used from time to time, arc sine. Very rarely, but I have seen it, a sine. I would steer away from using that one because it just looks like you're saying a is the coefficient of sine x. So I wouldn't use that one. Arc sine, yeah, you'll see that, and inverse sine of x. They're really the two that we'll see. Let's do some problems. We have to find the exact value of the inverse tan of root 3 minus the inverse tan of 1. But now we're dealing with a function. Remember, we've created inverse functions. So there is only one possible answer for the inverse tan of root 3 and only one possible answer for 1. Unlike when we were solving trig equations where we could get multiple answers for the angle. With inverse trig here, we're saying no, there's only one possible answer. So root 3, okay. What is the angle? Tan of what is root 3? Now, we give these answers in radians. We don't usually write them in degrees. The answer, because this is an actual value. It is a number. It's 60 degrees, but that would be pi on 3 radians. And they are very different numbers. Because you can't say 60 is the same as pi on 3. Well, it's not. Because pi on 3 is 3.14, etc., divided by 3. They are very different numbers. So you always give your answer to these in radians. So pi on 3 minus pi on 4, which works out to be pi on 12. Inverse sine of 1 on root 2 minus the inverse sine of minus a half. There's a couple of ways I could do it. This way, what I've done, well, 1 on root 2 is nice and easy, that's pi on 4. But inverse sine of minus a half, remember there's only one possible answer, so you have to think about what is the range of the inverse sine function. The inverse sine function could only give us answers that are acute or negative acute. So therefore minus a half, I don't give the second quadrant answer, it's minus the acute angle. So minus pi on 6 is the answer to the inverse sine of minus a half, and then when I play around with that one. The other way I could have done it is I could have used that property that the inverse sine of minus a half would be the same as minus the inverse sine of a half, and you'd still get the same answer. Find the cosine of the inverse sine of 40 on 41. Remember, inverse sine is representing an angle. So it's saying the cosine of this angle, whatever it is. Okay, I guess you could go to your calculator and work out what is the angle and then find the cosine of that. But there is a quicker way, really. Because if that's representing an angle, I'll just go to the right angle triangle and say, well, imagine that's the angle. And therefore, 40 over 41 is opposite over hypotenuse. A little bit of Pythagoras, I can easily work out the third side is 9. And all I'm really saying is, well, what's the cosine of that angle? Oh, it's 9 on 41. I just read it straight off the triangle. What about if it was the other way around? The inverse sine of the sine of 5 pi on 6. The answer is not 5 pi on 6. Because normally we say, well, an inverse will cancel with the original function to leave you with the answer. But this one can't, because the inverse sine function, remember, can only give us an acute or a negative acute answer. So it can't give me the answer of 5 pi on 6. I have to work out, well, what would be the equivalent answer? Now 5 pi on 6 is in the second quadrant, so it would give me the same answer as the positive acute angle. If this had been, say, inverse sine of the sine of 7 pi on 6, which is in the third quadrant, I'd say, okay, that's negative, so I want the negative acute angle would be the answer to that one. So you just got to be careful with that sort of one to make sure you're giving the answers in the correct range of answers. So 17b, we'll play with these new inverse trig functions.